Recording, right? Is it already started? How do I know?
There's a red
recording
Started, right?
Yes, yes.
the red color.
Yeah, I think we can start now. So welcome to the APRG seminar this week. We are happy to have Amudhan Krishnaswamy from Delft University. See, he's going to talk about local and multilinear non-commutative, the Leeuw theorems. Yeah, Amudhan, you can.
Thank you very much. Thank you very much for the invitation. And thank you all for being here. So this is joint work with Martin Caspers, Bas Janssens, and Lukas Miaskowski. All of them are at TU Delft. Okay, so let's just begin. So some background. This is, I'm sure, stuff you all know, but it's useful to say it again. So as you know, for a function on the real line, you can define a Fourier transform, right? And the Fourier transform looks like this. It's the integral of f of x times something, e to the something. And so given some function, which commonly these functions are called symbols on the real line, you can do a multiplication. You can do this multiplication at the level of the Fourier transform. So that defines this Fourier multiplier operator Tm, which is acting on the level of the Fourier transform. It's a multiplication operator on the level of the Fourier transform. So it's really the it's a multiplication operator composed with the Fourier transform and its inverse, right? And these sort of operators are very common. They are of great interest. So for instance, the Hilbert transform can be seen as a Fourier multiplier. With respect, the multiplier symbol in that case is the sine function. And usually, so one direct thing we get is that if you have a function which is in L infinity, then using Plancher's theorem, it says that the norm of a function and the norm of its L2, the L2 norm of a function and the norm of L2 norm of its Fourier transform are equal. That directly tells you that the Fourier multiplier operator is a bounded operator from L2 to L2, bounded above at least by the L infinity norm of M. And in general, it's a problem of great interest as to find out for which classes of functions M is this Fourier multiplier operator. When is it a bounded operator on LP for P not equal to 2? And there are various results. So, for instance, there's the classical, these Hoymander-Miklin type results, which give conditions which tell you something like if the function has smooth enough decay and its derivatives have smooth enough decay of all orders, then the associated Fourier multiplier operator is bounded on LP to LP. And there are various results in this direction. Now you can do this more generally on abelian groups. There's nothing restricting you to R. So if you replace R with a abelian group, you now have to look at its dual group, right? So this is the group of continuous homomorphisms from the group to the unit circle. And now the Fourier transform, as you think of it, it gives you a function on the dual group. So given a function on the group, you get a function on the dual group, and it's precisely this. And so in the case of R, you get this back because the characters are just the continuous homomorphisms to the circle are precisely of the form e to the power ix something. So and where mu is the hard measure. Now you can do precisely the same thing. You can define a Fourier multiplier operator. You can ask for a Plancherel theorem, and there's a LP boundedness problem, which is for which M is this going to give a bounded map. But really, so what if we want to go from the abelian case to the non-abelian case, right? So, okay, I'll come to that in a little bit. But before that, since we have something defined with respect to a group, it's natural to ask, how does this behave with respect to subgroups and quotients? So if you have a subgroup of a certain group, for instance, so if you, so this is the content of the so-called Leeuw theorem, which he proved in 1965, and then I think Psyche generalized it to all locally compact abelian groups later, which just says that if you have a discrete closed subgroup of a locally compact group, and if you have a function which is the symbol of a bounded LP multiplier, then the restriction of this function, of this symbol, that defines a bounded Fourier LP bounded Fourier multiplier on the appropriate space, and its norm is in fact bounded above by the norm of Tm. So and similarly, with respect to you can take quotients, and taking the quotient mapping also makes this behave well. So that's the content of this periodization theorem, which is that if you go to quotients, then that's equivalent to looking at the norm of the periodic function which gives this. So in particular, this lets you go from multipliers on R relate nicely to multipliers on the unit circle, if you have periodic multipliers, periodic symbols. Sorry, and he also did this compactification result, which is that you can discretize your group. So if you, instead of the whatever topology the group came with, if you equip the group with the discrete topology, and then look at the Fourier, you can look at the Fourier transform on that and look at the Fourier multiplier operator on that. Then the norm of the Fourier multiplier is in fact the same as the norm of the Fourier multiplier on the discretized, on the dual of the discretized group. And it's called the compactification result, because if you have a discrete abelian group, then its dual group is going to be compact in the okay. Now to the non-commutative case, right? So if you have a non-abelian group, what can you say? Now you want to replace it. You can't work with this homomorphisms from the group to the circle anymore, because it doesn't really capture much information about the group. In the abelian case, this gave us a lot of information, because these are, after all, the irreducible representations. So it does give a lot of information. The idea here instead is we have some sort of commutative function algebra, L, which is L infinity of G hat. The idea is to, in this quantization, to get to the non-abelian setting, is to replace it with a certain non-commutative algebra. And the appropriate thing is the group von Neumann algebra. So this is just, so if you have the left regular representation of the group, which acts on functions by left translation, then the group von Neumann algebra is the weak star closure of this set of operators. So you take this set of operators sitting inside the bounded operators on L2 of G, and you take the weak star closure of this, or the bicommutative of this. And this is in fact the appropriate algebra to replace L infinity of G hat with, because the first thing you note that if you have a function say a compactly supported, continuous compactly supported function, you can define, say, something called lambda f. And by this, I mean you integrate f with respect to lambda x. Now, lambda x here are these left translation operators. So you interpret this integral as a strong integral or something, as a limit. Then what you can check is lambda of the convolution of two functions at the group level. That is the product of these two functions, these two operators, lambda f1 and lambda f2. And this is precisely, this should remind you of what goes on with the Fourier transform and convolutions, right? The Fourier transform and convolutions relate to multiplications in exactly this way. And by this analogy, we think of lambda f as in fact being the Fourier transform of f. And in fact, using this identification, you can show that if the group is abelian, L infinity of G hat is in fact isomorphic as a one-Neumann algebra to the group one-Neumann algebra LG. So this is the L infinity space we are now working with. This is what replaces G hat. There's no underlying dual group, but there's a group one-Neumann algebra instead. And we can also define non-commutative LP spaces associated with these, because the group one-Neumann algebra, it has a weight. So in particular, if the group is unimodular, this is in fact a trace, and it's just defined by the condition that if you take a function, if you take an operator which looks like lambda of f, so it looks like the Fourier transform of f, then the trace of this should be the function's value at the identity. And so for a unimodular group, this lets us, well, you can do this in the non-unimodular case as well. I'm doing this for simplicity in the unimodular case because constructing these LP spaces in the non-unimodular case when this is a weight is a little bit more complicated. But so in the unimodular case, when this is a trace, the non-commutative LP space, by this I mean it's the completion. You take the set of bounded operators inside this one-Neumann algebra and you define a norm, the P norm, which is you're taking the trace of the absolute value of x to the p as an operator to the power 1 over p, right? And you take the completion of this space with respect to the norm, this p norm. And this is an LP space. We could call this space, by analogy, call this space LP of G hat. There is no underlying group G hat now, but by abuse of notation, we'll just say this is LP of G hat. And these are in fact just like LP spaces. These behave very well. So, for instance, the lambda of the convolution, the space of convolutions of compactly supported functions, continuous compactly supported functions, this is dense inside this space for all p between 1 and strictly less than infinity, and it's weak star dense in for p equal to infinity. And you have a Plancherel identity as before, that the L2 norm of a function and the L2 norm of its Fourier transform are equal. And you have a Holder inequality, and you can do interpolation just like you can do it for regular LP spaces. So everything is nice. These are good candidates for to talk about Fourier transforms, and sorry, to talk about Fourier multipliers. So just as before, if you have a function now you have a multiplier from the group. If you have a symbol on the group and you have some function, again, you can define the Fourier multiplier operator, which takes lambda f to lambda of m times f. Here, the multiplication is happening at the function level, right? Which can also be written as the integral of m times f times lambda. And from the Plancherel theorem, again, we get that if you have an L infinity function, then its L2 to L2 operator norm is in fact bounded by the L infinity norm of this function. And just as before, you can ask a more general question. That is, when does this function define a bounded map on LP of G hat? And there's been lots of previous work in this on these type of problems. So the earliest is probably by Cowling and Hargroup. They did this. Theirs was on for p equal to infinity. So these were now Fourier multipliers acting at the level of the von Neumann algebra itself. You're looking at completely bounded multipliers, and they characterized what some of these completely bounded multipliers look like for certain Lie groups of, I believe, real rank 1. But more recently, for instance, last year, there have been Heumander-Miquelin type conditions for, say, SL and R. For free groups, there have also been some sort of Heumander-Miquelin type conditions, which determine when these functions define a bounded map. But what, as the title of this talk suggests, that's not the thing we're going to focus on. It's going to focus on these dilute type theorems, which is how does this behave with respect to subgroups? So say you have a discrete subgroup of a locally compact unimodular group. Then Caspers, Parcet, Perrin and Ricard showed in 2014 that there is in fact a Leeuw type restriction theorem in this setting, that if you have, assuming that this group has some sort of something they call the small almost invariant neighborhood property with respect to this subgroup gamma, then there is a Leeuw type restriction. So the restriction of a symbol gives a bounded Fourier multiplier on the appropriate space. So examples, for instance, of groups which satisfy this condition are when the group is unimodular and the subgroup is amenable. So in particular, if the subgroup is there's a nilpotent group, for instance, or in abelian group, this still works. You can also talk about multilinear Fourier multipliers. It's a short generalization. So if you recall the previous definition we had for a single variable, the Fourier multiplier looked like you were integrating m times f times lambda. Where this was some integral of operators. You can define a multilinear Fourier multiplier. Just the natural extension is just to say that it's the integral of m, where m is now, instead of a function of one variable, it's a function of n variables on the group. And then you integrate all of these functions fi, and you integrate lambda of the product of these variables S1 to Sn, right? And this is what you call the multilinear Fourier multiplier associated with this symbol. And you say that it's a P1 to Pn to P multiplier if that if it determines a bounded linear map on the product of these spaces to LP. So in particular, well, this is a natural definition, because if you take a function, a so-called rectangular function, which looks like m1 of x times m2 of y, then the multilinear Fourier multiplier corresponding to this looks like the pointwise. It looks like the product of the linear Fourier multiplier Tm1 acting on lambda f1 times the multiplier of Tm2 acting on lambda f2. Okay, now multilinear multipliers, these have been studied. There has been some previous work in the, say, abelian or Euclidean setting, but even there they don't quite behave like the linear ones. So for instance, there's no natural set of pi for which a bounded function defines a bounded multiplier, right? Because you don't have a Plancherel type theorem for these products. So for instance, there's this result that the characteristic function on the disk in R2, if you consider it as a function of two variables on R, this is a bilinear multiplier. This defines a bilinear multiplier for a large range of pi. But if you consider the characteristic function as a single variable function on the group R2, this is in fact a linear multiplier if and only if p is equal to 2. So this result by Pfefferman. And there's this pretty huge result in '97 by Lacey and Thiel, where they showed that the bilinear Hilbert transform, which is also an example of a bilinear Fourier multiplier, this is bounded for a large range of pi, but it's still a completely open problem to find even some range of pi where the trilinear Hilbert transform is bounded. Luckily, there are multilinear analogs of these Leeuw theorems. Restrictions, everything still works perfectly well, even in the abelian setting at least. But the non-abelian case really seems to be completely unexplored. Okay, so I mentioned this, I mentioned this small, almost invariant neighborhood property. Let me precisely define what this is. This is, as the name suggests, it's sort of measuring how much open neighborhoods of the group are moved around by elements of the subgroup. So you're looking, if you take some neighborhood basis, and you're looking at the difference, say the symmetric difference of conjugated with elements from the group, from some set F, and you see how much this is moved around, and it's almost invariant if if you shrink the size of your neighborhood in the limit, it's not moved around that much. So saying that this measure is 0 is saying that is equivalent to saying that the measure of S inverse Vs that is approximately equal to the measure of V in the limit. Okay, so this brings me to the first result, which is a local restriction theorem, where the idea is we can remove this previous condition that was there, this small almost invariant neighborhood property. We can completely get rid of this and still have a restriction result. So the problem is now this restricted Fourier multiplier is no longer bounded about just by the norm of the initial Fourier multiplier, but there's some factor. And this factor, in fact, depends on the support of this function, of this symbol. And this function C, which is dependent just on the support of the symbol, this precisely measures the failure of this small almost invariant neighborhood property. That is, C of the whole subgroup gamma is equal to 1 precisely if and only if the group is, in fact, has this small almost invariant neighborhood property. And we have, in fact, we have explicit lower bounds on what these C of certain nice, for if you have nice subsets of real reductive Lie groups, we have lower bounds on what this should look like. Okay, so let me define what this function C is. It's basically, so as I said, it's measuring the failure of this almost invariant neighborhood property. So if you take a subset of the group and you take some neighborhood of the neighborhood, so V in this case is supposed to be a neighborhood basis. Sorry, it's supposed to be a neighborhood of the identity. You look at how much the elements of this set move around this open neighborhood, this neighborhood V, relative to how big it was in the first place. And then you take the supremum of all of these so you first, if you take some neighborhood basis of the identity, and you take the lim_inf of these things, so you allow these things to shrink down essentially, and you look at what the lim_inf of this delta f of V is, and then you allow a choice of arbitrary neighborhood, an arbitrary neighborhood basis, and delta f is the supremum of what you get at the end. So from this sort of definition, it should make sense why this is measuring the failure of the small almost invariant neighborhood property. So Cu in particular is the infimum of the square root of these delta f's, where f's are finite sets inside U. Okay, well, the details are not terribly important. I just wanted to show this so that it's clear how it's related to this small almost invariant neighborhood property. And as I said, we have quite explicit estimates for when the group is a real reductive Lie group. In other words, if the Lie algebra associated with the group, if you can write it as, say, the direct sum of a semi-simple Lie algebra and an abelian Lie algebra. That's what I mean by reductive. So, for instance, SLNR is an example of such a group. If you look at a ball of radius rho in the adjoint representation, so any element of the group determines a linear map on the Lie algebra, which acts by which takes x to gx g inverse, right? This defines the adjoint representation, and you look at what the norm of this as a linear operator is. Well, this makes sense because the Lie algebra in particular there's a associated invariant bilinear form on this Lie algebra, which lets you define a norm, which lets you talk about norms of linear operators on this. So if you look at this ball of radius rho, all group elements whose adjoint representation norm is less than rho, then the delta function associated with this set is bounded below by the radius rho to the power negative d over 2. D here is the maximal dimension of a nilpotent orbit. So you take a nilpotent element in the group and you look at the orbit it generates in the Lie algebra, and you choose the element which generates the Lie algebra of the maximum possible dimension. It generates an orbit of the maximum possible dimension, and that's the D here. So for instance, if the group is compact or abelian, D is in fact 0. So you get delta is greater than or equal to 1. And this precisely, well, this fits with the fact that abelian groups, for instance, have this small almost invariant neighborhood property because everything is invariant under conjugation. For SLNR and GLNR, these are this number D is n times n minus 1. For SLNC and GLNC, it's 2 times n times n minus 1. Okay, so here's a short proof sketch for how this works in the linear this restriction result. So if you have this small almost invariant neighborhood property, in these earlier result by Caspers, Parcet, Perrin and Ricard, what they rely on is showing that there's a net of contractions acting on the level of these non-commutative LP spaces, which goes from the LP space of gamma hat to the LP space of G hat, so that whenever you have a function whose support is contained inside this set F, these contractions in the limit, these contractions behave like asymptotic isometries in the limit. And further, they also asymptotically intertwine between these linear multipliers Tm and the restricted linear multipliers Tm restricted to gamma. And this is in fact the crux of the theorem. This lets us estimate what Tm, the restricted Fourier multiplier acting on some x, for some particular class of x, it lets us estimate the LP gamma hat norm of this, because all of these are contractions, and in the limit as well, they act like they are asymptotic isometries. So really, this is the backbone of the restriction theorem in the linear case when you assume the small almost invariant neighborhood property. The local result is really exactly this, except we just show that now you can get contractions which are, you no longer have asymptotic isometries, but you have that these contractions are bounded below by some factor delta f to the power 1/2. And this is the factor which shows up in the estimate we have for the linear case. We have the C, and C is in fact some delta f to the power 1/2. Okay, that's there's of course more which goes into actually getting these, but I'm not going to go into that. So yeah, in order to get the estimates for these delta f, really the idea is to get suitable neighborhood basis of the identity, and to do so, we start at the level of the Lie algebra. So you first take some.
Excuse me.
Yeah.
Will you go to the earlier slide?
Yeah.
Previous See this condition that no, next slide.
Yeah.
The limit. So such a condition.
Yeah.
I'm familiar with amenable groups.
Yeah.
It almost looks like amenable. So you know Fallner's condition.
Yes. Yeah.
Is it related to what the condition which you are giving here?
No,
Because
I wouldn't. No, I wouldn't say it is related to this. Okay. It is somewhat related because if you certainly if the group you're starting with is amenable,
right. This is turns out to be one or what?
this turns out to be one. So yes, so yeah, in that sense, yeah, it is related. Yeah.
Okay, thank you.
Yeah, so to actually estimate these things in the case of reductive Lie groups, the idea is you get neighborhood bases at the level of the Lie algebra, and then you take the exponential to go to the level of the Lie group to get a neighborhood basis there, right? So if you decompose your Lie algebra as the sum of the semi-simple part plus some center, you look at these G invariant neighborhoods, these tubes, G invariant neighborhoods in the Lie algebra, and you intersect these with some bounded sets, bounded balls of radius r and capital R and small r, to get some sort of symmetric neighborhood basis, which we call V epsilon capital R small r. And because these deltas are defined in terms of taking some neighborhood basis and then looking at how these limits behave, from the definition we have that delta of this of any set really is bounded below by this limit, assuming it exists. But the hard measure of sum of this set over here at the level of the Lie group really in the limit is equal to the Lebesgue measure of these neighborhoods we constructed at the level of the Lie algebra. And this is nice because now you have the Lebesgue measure is of course much easier to work with. And so we can show that this limit of which in terms of this Lebesgue measure really depends only on the semi-simple ideal. So we may assume that the center is 0, or in other words that the group itself is semi-simple. And in particular, if you take a set from this ball of radius rho, remember this ball it's the set of all elements in the group whose such that the adjoint representation, the adjoint operator corresponding to G, that has norm less than operator norm less than rho. And because of that, it's quite direct that G acting on these sort of sets is in fact contains the set V epsilon R over rho. And so now we are just estimating what the Lebesgue measure of these sort of sets, the limit of the Lebesgue measure of these neighborhoods looks like. And nothing involving intersections and so on. We're just estimating this. This does take some work, but we can show that the limit of this is this factor rho to the negative d over 2. I'm not going to get into how it is a little involved. We use for instance, we use the Harishchandra integral formula to show that the volume of these things, it scales like the Liouville volume of the symplectic manifold corresponding to the orbit of some nilpotent element. which is why you get this factor rho to the negative d over 2. But I don't think I have time to go into all that. But please look at the paper if you're interested. Because I also want to talk about the other part of result, which are these multilinear generalizations. So as I said, these they don't seem to have been studied much at all in the non-abelian case. And we get a precise analog of the linear case. Unfortunately, we could not get rid of this small almost invariant neighborhood property. But assuming this, you have exactly the same restriction result, that the restriction is also a bounded Fourier multiplier bounded above by the norm of the original Fourier multiplier. So the difficulties here really are that, as I said before, there's no natural range of pi for which these define bounded operators. So one big tool in the linear case is the fact that since these are bounded symbols, and we know definitely that it's a bounded Fourier multiplier on L2 to L2, you can do interpolation, and that gives you quite a lot of freedom to do things. That freedom, you don't really have this in this case. So the idea is to somehow reduce it to the linear setting again, by the fact that so here's how this sort of works in the n is equal to 2 case, right? So if you take a function and you convolve it from the left and you convolve it from the right by some function, you can show that this two-sided convolution, provided this function you're convolving with is suitably nice. So if it comes from the Fourier multiplier, comes from the Fourier algebra corresponding to this group, for instance, this convolution, this again defines a bounded P1, P2 multiplier for all range values of Pi. Once you do this, you can also rewrite the multiplier corresponding to this m tilde and show in terms of some Bochner integrals, or so in terms of some integral corresponding to nested linear multipliers. And so using this, you show first that for these sort of m tildes, you have a restriction theorem using techniques from the linear case, and then we show that these TMs can be approximated pointwise by these TM tilde by choosing suitable phi, and the phi we choose is really the idea is to choose functions which shrinking support, but still whose L1 norm is 1. So these sort of delta peaks. If you choose these sort of phis, you can approximate these original Fourier multiplier pointwise by these sort of nested linear things. And the result follows once we show that this behaves well with the restriction result in the nested case. So we also have a few other multilinear results. We have a lattice approximation theorem, for instance, which says that you can go the other way, that if your group is in fact approximable by discrete subgroups, that is, if you have a sequence of discrete lattices which fill up the whole space, which fill up the whole group essentially, or in other words, that the neighborhood, that the fundamental domains which these lattices define, if they form a neighborhood basis of the identity, then the norm of the initial multiplier is in fact less than the supremum of the norm of the multiplier restricted to each of all these lattices. And there's also a multilinear compactification theorem, although this is not much of a change from the linear case in terms of the proof, which tells you that you can, just like in the abelian case, you can go between the group and the discretized group. But there's a restriction in that to go from to say that the norm of the multiplier on the discretized group is less than the norm of the initial multiplier, you really need that the discretized group is amenable. And to go the other way, you need that it's approximable by discrete subgroups. And we also have a periodization theorem which says that it behaves well with respect to quotients. Again, to go one way, you cannot expect much. You really need, you have to go back to the abelian case in order to say anything about, if you're saying that the norm on the quotient group is going to give you any information about the norm on the group itself, then you really need that the group is abelian. This is really because you can, it's possible to construct groups with, it's always possible to construct non-abelian groups where this part is pretty badly behaved. And if you want to go the other way, you need a compact group. Okay. So we also have some results about cross products, which is that if you have two countable amenable groups and you have the cross product, which you have some action on of one group on the other, and you have a cross product, then you can sort of get multipliers on the cross product from multipliers on just one of these groups. So if you have a function just on two copies of your initial group, and you look at this function capital M, which ignores the other variables and just looks at which ignores whatever happens to gamma and is only concerned with what happens to the group lambda, then the multiplier corresponding to this symbol on the level of the cross product, that's going to define a bounded Fourier multiplier, which is bounded above by the norm of the Fourier multiplier, now not acting just on this group lambda, but really it's a vector valued Fourier multiplier. So these spaces are the vector valued non-commutative LP spaces with values in the Shat and P operators. So in other words, this is the non-commutative LP space corresponding to the von Neumann algebra of L of lambda tensor product with all bounded operators on some Hilbert space. So this theorem in particular, this theorem and this lattice approximation theorem, together with that, we get examples of multilinear multipliers on the Heisenberg group, because you're now saying that for something, the Heisenberg group is this, you look at it as the group of 3×3 matrices with one on the diagonal, upper triangular matrices with one on the diagonal. This can be seen, for instance, as a cross product of R2 with R. And so applying the previous theorem, we get that symbols of this form, which look like M of X, X prime, these define bounded Fourier multipliers, bilinear Fourier multipliers on the Heisenberg group, provided these M to begin with are vector value, bounded vector valued Fourier multipliers. And there are, again, there are some sort of Heumander-Miquelin type theorems which guarantee that as a vector valued Fourier multiplier, this is in fact bounded. I think I will stop here. Here are some references. So all of this is based on our work in the archive from January of this year. Caspers, Janssens, me, and Miaskiewski. And yeah. Thank you.
Thank you very much for a nice talk. Now we have plenty of time for questions. Are there any questions?
See, I can these results.
Yeah.
For instance, if can you push it to the direct products? If you have this result for G1 and G2,
Mm-hmm.
Can we say something about G1 cross G2?
Yeah, I think that should be possible.
So you are doing cross product.
Yeah. For the direct product, it should be possible. Well, certainly all the multilinear things, they will provided both of these have these small, almost invariant neighborhoods, then everything is fine. And yeah.
And these same groups, apart from amenable groups, do you have any good example of? See, we used to study sin groups, small.
Yes. Yes. So sin groups are examples of sine groups.
Whatever example comes to my mind is amenable. And see, all these results get through with higher rank groups also, isn't it? See, in SL2R,
yeah,
the nilpotent part, you may take the abelian part. It becomes abelian. Mark
yeah.
it one-dimensional. That D will be 1.
Yeah.
And when you go for higher rank groups, will it create problem or no?
No, I don't think it should create problems. In fact, the one thing we are interested in is so I think this thing, right?
Yeah.
So in fact, we are quite interested in SL and R because so far there are no nice examples of multipliers on SL and Z.
Okay.
Sorry, this is not directly answering your question. This is not your, but this, yeah. But I don't think higher rank groups should be a problem. I have to really look at it, but I don't know. I'm not sure this time.
No, the reason for me is this work of Colling and Hagerup.
Yeah.
It's very bad when you go for higher rank groups. Rank 1 is good.
Yes, that's correct. Yes.
So I was guessing.
Yeah. I think for them, I think they're showing even rank 2 they have quite bad.
Yeah, it becomes infinity. Yes. Yeah, thank you.
Are there some more questions? In case there are no questions, let's apply. Thank the speaker once again. Yeah, you can stop sharing. I'll stop.